seems to me that we got talking about, were you at this point?
Yeah.
Yeah.
We may mention the fact that a bond needs a bit of polarity to respond to the infrared. The pulsating electrical field passing a stationary bond causes that bond to oscillate in sympathy with that field as long as there's enough polarity of the bond, or polarity associated with the bond for that to happen. And so completely non-polar bonds are going to be pretty much invisible in the infrared. Okay, and you'll be able to, actually that's, to the real experts in infrared, that's instructive because they may be analyzing the infrared structure, and if they don't see a bond associated with what they think the structure is, that actually helps confirm what they think they're doing. And we would expect, for example, HF to have a very strong response because it's a very polar covalent bond. There are structures, for example, hydrocarbons, that are deceptively simple in terms of their infrared because what would you say about a carbon-carbon bond?
Non-polar.
Pretty non-polar, and the only polarity that's associated with it will probably be associated with the things that are attached to those carbons. And so there can be a tiny bit, but not much. And so very often hydrocarbons have simplistic infrared spectra because of that reason. Okay? This is the design of the old style infrared spectrometer. We have a glowing wire that serves as a source of infrared radiation, and it blasts all wavelengths in the infrared. And actually, it's designed so that the radiation is split into two paths, a sample path and a reference path, each of which passes through a cell. The sample cell contains the real stuff we're analyzing, and the reference cell is just designed to match this except not have the sample present as a control. These two beams then pass through, and they pass through a mirror. A rotating mirror used to be called a chopper, and it would just vibrate or spin, and it would alternatingly take a sample from this beam and then this beam, pass it through a monochromator. What's a monochromator? It's a wavelength selector. It's a device that selects the wavelengths. This thing would be under electronic control, and it would, as the sample is being analyzed, the monochromator would scan through the different wavelengths of the infrared, and then the alternating slices of data from the reference or the control side versus the sample side would hit the detector, and the detector would be mechanically controlled so that it would automatically subtract the reference cell from the sample cell and know the wavelength at which we were. Okay? And then that would be plotted out like this. And you're familiar probably with the appearance of the infrared spectrum. Okay, and recognize that what we call a trough or a valley is actually referred to as a band or a peak in the infrared. These things were notoriously difficult to work with. They were important, and every laboratory had them, but there were a lot of mirrors and optical alignments here that could come out of adjustment. In fact, they'd be sitting on the bench top, and some graduate student would walk up and bump it, and it wouldn't work. And you'd actually have to call service in and have them optically align all of the mirrors and the optical pathway for it to bring it back into adjustment so it would work. These things also took quite a while. They could take anywhere from 20 minutes to 30 minutes to run a scan. Today's instruments are much better by comparison. This is the design of the modern Fourier transform IR, or FT-IR. Again, we have a glowing wire as a infrared source, but along with the radiation coming from the glowing wire, right alongside of it is a laser beam. And a laser beam is bouncing off of the same optical path or mirrors and so forth that the sample is, and this is used to focus or automatically self-calibrate the optics. So you don't have to go in and do a lot of, now we still occasionally have to go in and do some adjustments and some repair, but the laser beam tells, the instrument is able to detect the intensity of the laser beam. And if the laser beam's intensity is beginning to fall off, that indicates that the instrument needs to adjust or rotate the angle of the mirrors and so forth until it optimizes. So it automatically calibrates itself. So we don't worry so much about the sensitivity of the optic path. This one's a little more sophisticated. When a beam from the glowing wire, it strikes a two-way mirror. That's not really a two-way mirror. I'm not real sure of the proper technology or terminology. But part of the beam passes through the mirror, part of the beam is reflected to create a split. The reflected beam strikes a mirror here that reflects it right back. And it passes through the mirror going this direction to our sample. This, coming along here, strikes this mirror and then is reflected off the surface and goes back. What we have here, and oh, by the way, this mirror here moves under electronic control. What this does is, we've got these beams coming back this way and beams coming back this way. They will be designed in such a way as to create an interferogram. What happens when you pass light through a pair of slits? You remember from the physics experiment?
It gives you all the same, it makes it, what's it called? It's all the same wavelength, it's all the same like that.
They do, but if the slits are comparable in distance apart to the wavelength of the light, on the back wall, behind the source of light, you get light and dark patterns. Do you recall ever seeing this experiment? This arises, I don't want to get too much into this, but this is the design of this thing, to select the wavelengths. So if I have a couple of slits, and light is coming through here, I might have to do a better job than that, sorry. And another beam is coming along through here like this. These two beams interact with one another, either constructively or destructively. You know what I'm talking about? Mm-hmm. And at certain angles, we'll get a bright spot back here, and certain angles, we'll get a dark spot. Dark spot is a consequence of destructive interference. The light spot is a consequence of constructive interference. You remember seeing this before? Mm-hmm. What this thing does is create that situation. So I've got these two beams that are coming together from either the reflected, the fixed mirror, or the reflected moving mirror, and by moving the mirror very precisely, I can create destructive interference and constructive interference that controls the wavelength. And with this angle business that we're talking about here with the slits is based on the wavelength of light. So different angles create different, it's based on the same type of interference pattern. Now, by moving this mirror in back and forth, I can control the beam or the wavelength of light passing through the sample. Does that make sense? Now, it requires a lot of mathematics. We use Fourier transform mathematics to translate the interferogram that comes out and convert it into a signal. And what we do is we run the background and collect that spectrum and save it in the computer, and then we run our sample and subtract the background from our sample. And that's what we work with downstairs. And these things run in a few seconds. Okay, they're very quick. You've probably already run infrareds before, and you know how this works. This is the basic design. Much quicker, much more efficient, much more effective. Now, it turns out that each type of bond responds in a different place in the infrared. We would expect carbon-carbon stretches to be fairly weak, and they are. Why? Not very polar. And in fact, the only polarity associated with these will be associated with the things that are attached to the carbon. They'll be slightly different. We'll create enough of a dipole so we'll see them a little bit. In general, a carbon-carbon bond will signal around, or will have a band around 1200 reciprocal centimeters. Carbon-carbon double bond, about 1660, and a carbon-carbon triple bond around 2200. Okay? And as this indicates, This signal will be probably absent or very, very weak if the triple bond is inside the chain. If it's on the end, we'll usually see evidence of it. But if it's buried in the chain, because of the lack of polarity, we won't see it at all. Okay? Now, conjugation lowers the frequency. What does conjugation mean?
Or it's like a
Yeah,
alternating.
alternating double bonds. So if I've got double bond, single bond, single bond, that kind of an alternating pattern. When we get into the, in some later chapters this semester, we'll look at the UV. And we'll look at the absorbance of double bonds with respect to conjugation, and we'll see that effect. So what this does is it lowers the wave number where we expect to see the double bonds. Isolated double bonds, 1640 to 1680. A little bit lower energy for the conjugated ones. And the aromatics, lower still. Aromatic rings have completely conjugated double bonds in 7-ring, 6-member ring. Carbon-hydrogen stretching, and this is important. When the carbons that are bonded to hydrogen are sp3 or single bonded carbons, we'll see them signaling, or we'll see them absorb infrared between about 2800 and 3000. If the hydrogen is attached to a double bonded carbon instead, you'll see it above 3000. So it's a subtle difference, but it's noticeable, and you can see it. If the hydrogen is attached to triple bonded carbons, the sp hybridized type of carbon, we'll see the band as a fairly intense, sharp band around 3300. And so this region between about 2800 and 3300 is a good region to try and gauge the general nature of the carbon backbone, whether or not there's double bonds, single bonds, or triple bonds. And there's some theoretical components here. In talking about chemistry in the past, have you talked about S character and P character? Okay, there's some greater percentage of S character will make the carbon-hydrogen bond stronger. That would mean how big, which is bigger, a P orbital or an S orbital? The S is a little bit, I mean the P is bigger, the S is a little bit shorter. So the greater the S character, the shorter the bond, the stronger the bond. That's what that's saying here. So we're going to see a stronger bond here and here than there. And that's the explanation that we use to describe the difference in position. All right. Here's an alkane. And notice that this is octane. And octane, normal octane, great big molecule, pretty good sized molecule. And the spectrum, even the fingerprint region, is pretty sparse. But here, this is real important to us. Here's 3000 right here, and notice that all of the bands are below 3000. That carbon-hydrogen stretch for a saturated or single-bonded carbon is going to be below 3000. Okay, and that's real diagnostic, real helpful to recognize that. Not very much else in that spectrum to look at. You see any 1200 carbon-carbon bonds? Not a one. Why do you think? It's not polar. Okay. Alkenes. Now, because of the presence of the double bond, a number of things happen. The double bond tends to create more polarity. A double bond contains sigma electrons and pi electrons. Those loosely held pi electrons create a little bit of charge separation, a little bit of polarity. And so we see the spectrum become considerably more complex. This is one hexene, and we see our saturated, our carbon-hydrogen bonds here attached to saturated carbons here below 3000, but we see a peak here